So first, let us look at the transmitter. Normally, whenever we are trying to transmit a signal that goes towards the satellite, right? It is considered as a uplink signal, right? So we need to have several what you call amplifiers, and you need also a lot of what you call most of the components are analog over here, and you want to input what you call lot of power to this so that it can transmit and take the signal until it reaches the satellite, right? It needs a lot of power. Yeah. Yes, correct. So uh, you should not lose the message, correct? So because of that reason, you are trying to send the message with a lot of power. So like that, so you try to send the signal with a lot of power, and you will make sure that the signal will be reaching the satellite. Right now, normally whenever we are trying to design such a system, right? The first thing to note is that uh, we are going to use several types of transmitters and receivers. Okay, so first one, let's look at what happens in a uh, uplink station. That is, you are trying to send something to uh, the satellite. Okay, so that is basically we have three parts. First, let me write the three parts names first. So the first part is the uplink station, right? We have some baseband signal, and I want to send this baseband signal directly to the satellite, right? So maybe my ultimate intention should be something like I want to get a good communication from one point to other point on Earth. But if this distance is too long, by means of sending through LOS, if LOS communication is not possible, right, over the Earth surface, right, then satellite communication is the other best option, right? Okay, so hmm, 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 hmm. Okay. Hmm, hmm. True. Correct. Right. If possible to build a LOS communication you on the Earth surface, it's better. It's good. Okay. But most of the times that may not work if the distance is more, right, on Earth surface. So because of other parameters, as you mentioned, so that communication will not work if the distance is large. So you have to go for the satellite communication, right? So line of sight you try to retain, right? Even in satellites, yes, the line of sight can be retained, right? That's why. So the first one is uplink station, from where you want to send something, and we have another system. The second part of this is in the satellite, and the one which receives, it's a receiver as well as a transmitter. Okay, this is present on the satellite, and this is called as a transponder. Okay, transponder, and then we have another station which receives the signal from the satellite, that is called as the downlink station. Okay, three parts we have whenever we are considering the satellite communication. So let's look at one by one. The first one is the uh, uplink station. Right. So the uplink station, its intention is to transmit the signal from Earth to the satellite. So during this process, it takes the input in the form of, say, baseband signal. That's input signal. Directly, it will go to a block called IF modulator. In whatever is the intermediate frequency, it gets converted onto that particular frequency, right? You are trying to normally this will be in some gigahertz range, right? Uh, so IF modulator will modulate the baseband signal into the appropriate intermediate frequency. As we know now, the baseband is something which is the which is in its original format, like speech, all right, or the photograph, or maybe right the any other audio signals, right, which we want to send, right. But that is in the lowest possible frequency range. It's a low pass signal or the baseband signal, right. To convert this into the IF intermediate frequency, right, you multiply by a high frequency carrier signal. Right. Whenever you multiply, you get two components. One is low component, one is high component. One, right. Even some other terms might come. Some of the mid-range frequencies are also available. You will pass only that which you want to set. Okay. Like in this case, I will write it as a BPF because most of the time, not a very high frequency you choose, not the lowest frequency also. You can choose the mid-range of frequencies. So we'll use a band pass filter. Yeah, relevant frequency which you want to send, right? Which that this actually depends on the available channel availability and the other resources as well. Okay, or if you are taking, if you are using a permitted band, right? You need some permission to use that. Anyway, let's say that you obtain the permission, but the frequency should be matching to that, right? So anyway, we have an upscaling coming up. Up converter will come after this, but this is in terms of intermediate frequency. We are choosing the specific band. Okay, using this PPF. So what comes out is the chosen IF frequency. Okay, this is the IF which we have chosen, intermediate frequency. But this is not the frequency which you transmit. You will not send this as it is. You need to convert this into the RF. Okay, so for RF we use a RF mixer. So followed by there is a mixer coming up. Let's write this as RF mixer. Now the job of this mixer is that you add the microwave components, right, to this. In the sense, I want the microwave power to be given. I have to give a microwave power to this. Okay, so uplink frequency related microwave generator will be there. With that, I am actually using this mixer. Okay, so this is uplink microwave generator. Right. This generates the microwave signal. With that we multiply. Okay, RF mixer will mix it. Once again, you have, since you are already in something like a mid range of frequency, maybe in the megahertz range. Okay, uplink with the microwave goes to the gigahertz range. You multiply by mega into giga, you get once again two or more bands. But it's already in a band pass, right? This is a band pass output, so you don't get a low pass at all, you get few more bands. So out of those bands which you have obtained, once again you need to choose the exact one which is allowed for transmission. Okay, so we'll use another band pass filter at the output. Okay, so this is another band pass filter. Okay, now you see this is actually the radio RF wave, because it is microwave, right? Now there is a specific name for these three components, right? When we club all the three components together like this, they are called as the up converter. It is an up converter. Okay, from the up converter, the output of this band pass is then connected to a very high power amplifier, right? Just to give the required power. Now its properties are not changed because message has been converted into high frequency, only the power is required. Okay, so you use a high power, right? From this high power amplifier, we are giving this to the transmitting end, from where it sends the signal to the second part in the SATCOM design, that is the transponder. Just a second, I'll show you the complete diagram. All right. So the baseband signal, which is in the original format of the message or a low pass signal, gets converted onto a high frequency first, right? Then gets converted on to we'll put that onto the microwave range of frequency, right? RF, right? Then select the appropriate frequencies out of it. Give a lot of power to that by using a power amplifier, right? Then transmit. Okay, so that is the first part. Now the second part. Yes. Now we'll look at the transponder. Okay. So the transponder is a transmitting and receiving element that is present inside the uh, uh, in the satellite. Okay. So here you will have one antenna, right, that is responsible for receiving the signal, right? At the same time, you have another antenna, right, which is responsible for the transmitting of the signal, right, from the now basically the transponder is not going to perform any sort of processing. Okay, but there is one thing it has to do. It's not simply receiving and sending it back, it has to perform a small amount of frequency translation because the uplink and the downlink frequencies are different, right? So whenever, yeah, for example, let's go to the previous. I just want to add a point here, right? The uplink frequency. Normally, this is in the range something around 5.9 to 6.5 gigahertz is the normal range. Okay, at the same time, the downlink frequency of the from the satellite to Earth, downlink frequency will be in the range 3.7 to 4.3 gigahertz. Okay, so zero point 0.6 gigahertz is the bandwidth available for uplink and downlink. Now you see the transponder receives this, but it has to send this, right? So the same message needs to be converted onto this, right? Message remains same. So this is the change, this is the work that the transponder has to perform for every message it receives. Only that's the job. No modification, no processing, right? No changing this, right? Only the frequency. This is, you are translating the signals frequency from one frequency to the other frequency, which are corresponding to the uplink frequency to the downlink frequency. This job it has to do. Okay, so now we'll go for, we understood the requirement, right? Let's go move to the diagram of a transponder. Okay, so inside this transponder, the first component is to use a band pass filter. Right. That band pass filter. Huh. Yes, exact frequency within that band, right? So we know that the uplink frequency is in this band, right? Like 5.9 to 6 point something, right? So it's in that range. I have to pick up the same thing. So you design a filter that is exactly matching to this. Okay. So yes. True. Right. So basically you have one antenna. This picks up the signal, right? That I'll directly write this as the uplink filter. This is a uplink signal. Okay, this is given as input to a filter. This is the input filter. Yeah, it's a BPF most of the time, right? Yeah, other techniques can also be used, right? So normally this particular filter is a band pass filter to select the required band of frequencies. All right. As soon as this is picked up, we will use a low noise amplifier. Okay. So that is, okay. And this low noise amplifier actually has two different parts. Okay. So the first part is specifically around the 6 gigahertz, right? That particular frequency you are trying to boost. Okay, so this I'll just write around 6 gigahertz. Right. Then You see, I need to bring the frequencies down, right? Approximately, you want to bring it down by a factor of 2.2. Why? Because 6 minus 2.2 is what your band is, right? So 6 minus 2.2 and 6 plus 2.2. Out of which, if I multiply this signal by a 2.2 gigahertz signal, I get two frequencies. One is 6 minus 2.2, right? And one more will be 6 plus 2.2, right? That I can actually use it to bring the signal down to the required range, right? Of downlink. 3.7 till 4.3 is my range. I want to bring it down. So what we do here is a another RF mixer. Okay, we use a mixer circuit, and this particular circuit takes another input, and that input comes from a local oscillator. So required frequency of this local oscillator approximately 2.2 gigahertz. Right now you see 6 plus 2.2, 6 minus 2.2, two frequencies will come at the output. Correct. So out of that, I have to select the appropriate frequency. Huh. Huh. Okay, okay. Yeah, please take your time. No problem. I'll wait. Yes. Absolutely fine. No problem. This local oscillator is required. Uh, correct. So the incoming frequency at the output of the low noise amplifier, right, will be multiplied with a 2.2 gigahertz local oscillator signal to get a low frequency and a high frequency component, right? Out of which, so we have one option here, right? Most of the time, they simply because the signal's strength is pretty much less over here, right? And either you can use a filter, right? Then followed by we use what is called as the amplifier. Okay, so select the only that frequency which you want, right? So how to select that? Again, I use a band pass. Use a band pass filter, right, centered around the required band of frequencies. So it will select that frequency. Then I need to put it into an amplifier, right? Only that. Yeah, yes. Around 3.7 to 4.3, whichever is the frequency that you are using, that will be amplified now. Okay, that comes at the output now because you tune this BPF to the central frequency of that band so that it will pass anything comes in the downlink frequency. Okay, and then I need to use another that is low noise amplifier. So this is around 4 gigahertz. Right. So now the signal is around 4 gigahertz. Now whatever comes at the output, right? Then the uh, transponder comes into picture where there is what you call as a multiplexer. You can actually multiplex multiple signals, right? So we need to use a multiplexer over here. just for the purpose of multiplexing the signals. Okay, you use multiplexer. This actually has multiple inputs, right? Multiple signals will come, it will multiplex them into a single signal. Okay, then it actually uses another amplifier at the output. Just this is the final amplifier, okay, just before the transmission. Okay, so it uses a specific amplifier, that is traveling wave tube amplifier. Okay, just to give enough amount of energy, right, power for the transmission, right? Now this signal is in the required range of frequencies for the communication. Okay, and this is approximately the we obtain the downlink signal here, right? So that signal gets transmitted in the form of the downlink signal. Okay, I'll show you the overall diagram. That looks like this. Yeah, this is from the transponder. So transponder received a uplink signal, that is the left, and it converts that into a signal which looks like a, okay, which is a downlink signal. Okay, now okay, let's move further, and now we will consider the block diagram of the third part, which is the downlink station. Okay, so we have the downlink signal coming from the transponder to the downlink station. Okay, so there will be another antenna to pick this signal, and this signal is the downlink signal will be picked up by this antenna. Okay, as we pick this, we are going to use, first we are going to use a band pass filter. Alright, so band pass filter signal is pretty weak normally. So in order to amplify that, we have to use it pretty much. Amplifier noise should be very less. That's why it's called as the low noise amplifier. Okay, the low noise amplifier. Now I need to bring it down to the low frequency. That is a bass band. Correct? So before bringing the bass band, we'll bring it to the IF range first. Okay. So to do that, I have to use another RF mixer. Correct. All right. So I multiply with the yeah, I'm going to use the microwave frequency, right? So that that gets added as well as that gets subtracted. Correct. So after subtraction, I get the IF, right? Okay. So you can see here we are going to use the microwave frequency generator. So the microwave frequency generator will generate the required microwave frequency. This is in RF. Okay, this is also RF. Now we multiply, mixer will generate two different RF frequencies, right? So one will be the highest one will be the lowest one, right? So the lowest one I can obtain by passing again, this is not in the what you call the baseband range. It's still not in the baseband. This will be in the IF range. The lower part will be intermediate frequency. So to select that, I have to use a BPF. Hmm. It will be yes, IF. The low frequency. Okay, only that will be selected. Right. Lower frequency band gets selected, right, and the higher frequency band gets eliminated. So BPF will do that. Now I have IF. I want to get the original message from this, right? So what we can do, you perform the demodulation, right? Basically, we call it as a IF demodulation, right? From the IF frequency, now you get the baseband signal over here. Again, we have a specific name for these three components altogether. We are bringing the signal down, right? Yeah, so this is referred as the down converter. Right? And so basically, this kind of representation of the satellite communication link, right? Starting from the conversion of the baseband signal into a RF frequency in case of the uplink station, and converting from the uplink signal to a different frequencies for downlink signal in the transponder, and then receiving back the downlink signal and converting it back to the original message format, right? This whole these three parts will actually try to build what is called as a space communication network, right? You have three different what you call components or nodes coming into picture. There is one concept called as a deep space network. Okay, so the deep space network, the fundamental units of a deep space network includes the same three components which we have which we were looking so. Okay, then this actually can be further extended, right, to include many more base stations receiving the signal. So you can actually this could become something like a huge network as well, because there could be communication between the satellites as well. Transponder can actually send and receive the messages from the neighboring what you call satellites as well. Okay, also this could include the communication that might happen or that might be required to have whenever there is a space mission to some other planet or something, right? So you see that there will be a communication from the space vehicle to that satellite will send it back to earth. Okay, something like that. You see that this can be a extended to up to any level of networking. There is a networking coming into picture, but as of now in the communication part we will not look at that networking, but just remember this term that is called as a uh, deep space network. Okay, so which is the network that you can build using satellite communication, like how we use internet as a networking tool, right? So similarly, there could be another network of varieties of transmitters and receivers present in the transponders, plus the earth station base stations, and the vehicles, space vehicles, right? All of them together can be clubbed to form a deep space network. So what are the functions over here, right? So all the equipments that you need to use here dependent on, right, what is the functionality you want to achieve. First thing is that. Then what is the type of service? Is it service based? If yes, what type of service you want to provide? Maybe just you want to monitor something, like a surveillance, or you want to right, keep track of something. That's it. These are the services. And when we say we are using the communication, there has to be a specific usage of bands of frequencies, right? So it also depends on that. Then what type of transmitters you are using, right? What type of receivers you are using, what is the antenna characteristics, etc. Okay, so basically the three components which we have uh, uh, studied today, they have to be integrated based on all these parameters, right? Okay, then normally uh, there could be subcategories under this, under the satellite communication topic. Something like one of them could be like you want to use the satellite communication for both transmit and receive. Okay, possible. Second one is that you may want to use it only for receiving purpose, right? You will keep receiving, you don't transmit. And the third option will be only transmit. I transmit, I don't want to receive anything. I want to keep giving the message to someone else, right? There is no question of reception, right? Like this, you have the either one-way communication or the two-way communication that is supported for the satellite communication. Okay, and we also have another representation which can actually receive as well as the transmission. Both will happen here. Okay, from where we pick up and from where we are going to deliver. Something like, let's say we have an antenna that picks up the signal that is coming from the satellite. Okay, maybe it's around the 4 gigahertz. You just need only that part of the circuit. You don't have to build the whole circuit, right? You don't have to deal with everything, right? Every signal, you are not going to work on that, right? So that's why you use only that part of the circuit which is required for you, depending on your service. What service you provide, you just have to get that. Okay, then there is one more important aspect over here, that is when yeah, okay, what type of satellite you are trying to communicate with. This is important because there will be a relative motion, right? Because if you are using if you are trying to establish the communication between the base station and the stationary satellite, geostationary satellite, then you see relative motion will not come into picture. Okay, right. At the same time, if you are trying to communicate with with a satellite which is not geostationary, you see Earth is rotating, plus that satellite is also moving on its path, right? Now you see you have what is called as a relative motion. So as soon as you have a relative motion in place, right, there is a specific what you call effect that comes into picture called Doppler effect, right? So both your uplink and downlink channel looks like a different frequency whenever, right, whenever there is a relative motion, depending on whether you are moving away or you are moving closer, right? So as we know now, if I am receiving a signal and I am coming closer, it looks like a larger frequency than what it is, right? At the same time, if you are going away, you feel that Yeah, it's smaller than the actual frequency, right? It appears like that. So we have to avoid that. So under those conditions, both the transmitters and receivers present in the satellite as well as inside the earth station, correct? Because you are receiving something, right? Wherever you receive, there is a problem. Transmission, no problem. So receivers are present where? In the satellite and in the receiving station. So both of them should be well equipped with a circuit called as the Doppler extractor. Okay, this is important because you want to eliminate the effect, Doppler effect, right? So normally we have another supporting tool that is called as a telemetry recovery, right? So these two components will help you in what you call correcting the received signal. Okay, corrected Doppler corrected signal will be coming. I'll just show you where it's going to happen. Okay, so in this circuit you are supposed to add, right? So as soon as you receive something, you will do that. The BPF will come later. Okay, this BPF will be coming later. Before that, I'll make the modification, right? Whatever signal I receive, I correct that. I'm going to perform the Doppler's correction, right? Two components. One is a Doppler extractor, and the second component is telemetry recovery. Right? These are required to make a correction when you receive a signal from a satellite which is moving with respect to Earth. So there are two types of motions. One, maybe the Earth can be considered as a stationary and only you consider the movement of the satellite, or you will consider both. Satellite is also moving, Earth is also rotating. Maybe this comes into picture whenever there is opposite direction. Okay, Earth is rotating in one direction, satellite moves in the opposite. Then this effect is more. Okay, if they are moving in, both are moving in the same direction, only relative motion comes into picture. Okay, so Ah, Doppler apps. And the second one is a telemetry recovery. Okay, telemetry recover. Yeah, recovery. It will recover the telemetry related data. So club the together two components results together to get the correct Doppler corrected output. Sorry, Doppler corrected output. So it will also help you in estimating the various parameters related to the what you call satellite as well. You can keep track of the satellite by measuring its velocity, right? It's various parameters, right? Etc. Can. Hmm. Okay, okay. So there, definitely it is required, right? So you need to keep track of something. So what's the velocity? What time, right? How to change the velocity if you want? How to control, etc. will come into picture. Then all these concepts will be helpful. Okay. So like that, actually this is there are many more topics in this, but as of now, I think this is sufficient, right? The basic block diagrams plus the one major issue of Doppler effect.